Welcome to this model. In this model, we are going to see about the wired LAN or Ethernet. In the previous model, we learned that local area network is a computer network that is designed for a limited geographic area such as a building or campus. Although a LAN can be used as an isolated network to connect computers in an organization for the sole purpose of sharing resources, most LANs today are also linked to a wide area network on the internet. The LAN market has several technologies such as Ethernet, token ring, token bus, FDDI, and ATM LAN. Some of these technologies survived for a while, but Ethernet is by far the dominant technology. Now, in this model, we are going to discuss about the IEEE standard project 802, and which is designed to regulate the manufacturing and interconnectivity between different LANs. We then will then concentrate on Ethernet LANs. Although Ethernet has gone through a four-generation evolution during the last few decades, the main concept has remained. So Ethernet has changed to meet the market needs and to make use of the new technologies. In 1985, the Computer Society of IEEE started a project called Project 802 to set standards to enable intercommunication among the equipment from a variety of manufacturers. Project 802 doesn't seek to replace any part of the OSI or the Internet model. Instead, it is a way of specifying the functions of physical layer and data link layer of major LAN protocols. The standard was adopted by the American National Standard Institute, that is ANSI, ANSI. In 1987, the International Organization for Standardization, ISO, also approved it as an international standard under the designation ISO 8802. The relationship of the 802 standard to the traditional OSI model can be seen in this diagram, that is this diagram. So the IEEE has subdivided the data link layer into two sublayers, that is LLC and MAC, that is logical link control and media access control. The IEEE also has created several physical layers standards for different protocols. And the data link layer, that is the data link layer in the IEEE standard is divided into two sublayer, as I said earlier, that is LLC and MAC. We said that the data link control handles framing, flow control, and error control. In IEEE Project 802, flow control and error control and part of the framing duties are collected into one sublayer called logic link control. Framing is handled in both LLC sublayer and MAC sublayer. The LLC provides one single data control protocol for all IEEE LANs. So in this way, the LLC is different from the media access control sublayer, which provides different protocols for different LANs. A single LLC protocol can provide interconnectivity between different LANs because it makes MAC sublayer transparent. And framing means, that is, for example, LLC defines a protocol data unit, that is PDU, that is somewhat similar to that of HDLC. So the header contains a control field like the one in HDLC, and this field is used for flow and error control. The two other header files define the upper layer protocol at the source and the destination that uses the LLC. These fields are called the destination service access point and source service access point, that is SSAP. The other fields defined in the typical data link control protocol such as HDLC are moved to the MAC sublayer. In other words, you can say that a frame defined in HDLC is divided into PDU at the LLC sublayer and a frame at the MAC sublayer. And the purpose of the LLC is to provide a flow and error control for the upper layer protocols that actually demand these services. For example, if a LAN or several LANs are used in an isolated system, LLC may be needed to provide flow and error control for the application layer protocols. However, most upper layer protocols such as IP do not use the services of LLC. So the multiple access methods including random access, controlled access and channelizations are used in MAC, that is media access control. And IEEE Project 802 has created a sublayer called media access control that defines the specific access methods for each LAN. For example, it defines CSMA CD as the media access method for Ethernet LANs and token passing method for token ring and token bus LAN. And in contrast to the LLC sublayer, the MAC sublayer contains a number of distinct models. Each defines the access method and framing format specific to the corresponding LAN protocol. The physical layer is dependent on the implementation and type of physical media used. IEEE defines detailed specifications for each LAN implementation. For example, although there is only one MAC sublayer for standard Ethernet, there is different physical layer specifications for each Ethernet implementation, which we'll discuss hereafter. Okay. And now let's move on to the standard Ethernet. In the original format or Ethernet was created in 1976 at Xerox Palo Alto Research Center, that is Spark, and since then it has gone through 4 generations. Standard Ethernet 10 Mbps, fast Ethernet that is you can see in this diagram, right? Fast Ethernet 100 Mbps, gigabit Ethernet 1 Gbps, and 10 gigabit Ethernet 10 Gbps. And in MAC sublayer, that is in standard network Ethernet, the MAC sublayer governs the operation of the access method. It also frames the data received from the upper layer and passes them to the physical layer. The Ethernet frame contains 7 fields: preamble, SFD, DA, and SA. That is length or type of the protocol unit. Okay. And this CRC, that is the cyclic redundancy check, and Ethernet doesn't provide any mechanism for acknowledging the receive frames, making it what is known as the unreliable medium. Acknowledgements must be implemented at higher layers, and the format contains some fixed formats like preamble, SFD, DA, SA, and so on. Now let us see one by one. The first field of the 802.3 frame contains 7 bytes, that is 56 bits of alternating zeros and ones. That alerts the receiving system to the coming frame and enables it to synchronize its input timing. The pattern provides only an alert and a timing pulse. The 56-bit pattern allows the stations to miss some of the bits at the beginning of the frame. The preamble is actually added at the physical layer and is not part of the frame. The second field, that is start frame delimiter, is 1 byte, which has the constant field that 10101011. It signals the beginning of the frame. The SFD warns the station or stations that this is the last byte last chance for synchronization. The last 2 bits, that is 11, alerts the receiver that the next field is the destination address. And DA field is 6 bytes and contains the physical address of the destination station or stations to receive the packet. And the SA field is also 6 bytes and contains the physical address of the sender of the packet. The length field is originally this field is used as a type field to define the upper layer protocol using the MAC frame. The IEEE standard used is as the length field to define the number of bytes in the data field. So both uses are common today. And the next one is data field, which carries the data encapsulated from the upper layer protocols. It is a minimum of 46 and a maximum of 1500 bytes. And CRC is for the last field, contains the error detection information. And the Ethernet has imposed restrictions on both the minimum and the maximum length of the frame. The minimum length restriction is required for the correct operation of CSMA CD. And Ethernet frame needs to have a minimum length of 512 bits or 64 bytes. Part of this length is the header and the trailer. And if we count 18 bytes of header and trailer, 6 bytes of source address and 6 bytes of destination address, and 2 bytes of length or type and 4 bytes of CRC. Then the minimum length of the data from the upper layer is 64 minus 18 for it corresponds to 46 bytes, right? So if the upper layer packet is less than 46 bytes, then padding is added to make up this difference. So we have to send 64 bytes, so padding will be done. The standard defines the maximum length of the frame as 1518 byte, and if we subtract 18 bytes of the header and trailer, the maximum length of the payload is 1500 bytes. So the maximum length restriction has two historical reasons. First is the memory was very expensive when Ethernet was designed. Maximum length restriction helped to reduce the size of the buffer. Second, the maximum length restriction prevents one station from monopolizing the shared medium, that is blocking other stations that have data to send. And each station on the Ethernet network, such as PC, workstation or a printer, has its own network interface card, and the NIC fits inside the station and provides the station with a 6-byte physical address. The Ethernet address is 6 bytes and normally written in hexadecimal notation with a colon between the bytes. For example, 06 colon 01 colon 02 colon 02C colon and 4B colons. And we have three type of address called unicast, multicast and broadcast. And source address is always a unicast address. The frame comes from only one station. And the destination address, however, can be unicast, multicast or broadcast. And we must know how to distinguish a unicast address and a multicast address. If the least significant bit of the first byte in a destination address is 0, the address is unicast. Otherwise, it is multicast. Unicast destination address defines only one recipient, and the relationship between the sender and the receiver is 1-to-1. Multicast destination address defines a group of address, and the relationship between the sender and receiver is 1-to-many. And the broadcast address is the special case of multicast address. The recipients are all the stations of the LAN. That is called a broadcast. Okay. And to find the type of address, we need to look at the second hexadecimal from the left. And if it is even, the address is unicast. If it is odd, the address is multicast. If all digits are F, the address is broadcast. Therefore, we have concluded a few points like the unicast address, because A is binary. For example, 1010, last bit is 0, so it is even. So you can say that it is a unicast address. If you are given with the address called 0111, we have to check the last byte. And if 011 means the last bit is 1, which is odd, therefore it is a multicast address. This is how we can find the type of address. Right. Thank you.